length scale and the variance, you can get it to separate pretty well. So let's go over and look at some code and try this data set of this credit data. So let me go over to the I just need to start my Jupyter notebook. Okay, let me share the code again. Right, so here's the Jupyter notebook, and so again we have the imports NumPy, matplotlib, and I put in this command here, matplotlib inline with a percentage sign for it to get my plots to be inside the notebook, so it doesn't create a external file. And here's the data set make moon, so that's what makes these things. So let me just let's just look at the same picture we got before. Yeah, so here's the a data set, and we tried different things, logistic regression, to separate them. And here's the one that we used SVC. So by default, if you use SVC in sklearn, then it will by default use an RBF kernel. So here we create an instance of the support vector machine, and we fit it to these data points here, and then we have this little graph program here that can sort of color the things, so we get a picture like this, which is what we had before. So let's go to this data set here. So we put it up. I put it up on the page, on the course page, so you have it. So we need to import pandas. So let's do that. And then we need to download the data sets. So if you download it from the page, you'll get some Excel file, and you can use pandas to load it into your program by using this pandas.read CSV. So it's actually an Excel file, but CSV is just as good. So we download it into the program, and let's just look at the beginning of the data set. So you can see here, what we have here is the data here for the loan data here. We have the applicant's income, his age, the size of the loan, and then we have this loan to income, which is just the loan divided by the annual income. And then we have the outcome of what happened there within 10 years, whether the loan was defaulted or whether it was paid back. So 0 means it was paid back, and 1 means it defaulted. And so we want to try to train an SVM, a support vector machine, to see if we can make a classifier that from these data, income, age, loan, and LTI, can determine or predict whether the applicant is going to default or whether we're going to get our money back. So we have this. There are 2,000 data points in this data set here. So we have the data vectors are 4-dimensional, right? There are 4 features, and we have labels here. Labels should be, and when we use support vector machines, should be -1 and 1. So here's the 0s and 1. So we have to do a little bit of engineering here to change the 0s to -1s. So let's try to split this data set into a training set and a test set. So we're going to train on the training set, and then we're going to test it out on the test set. So let's import the train test split that we have talked about before. That's the one that automatically creates a training set and a test set. So let's import that. And then I want to separate the labels and the data set. So I do that here by here. I only want to take again, I want to leave out the client ID because that's not going to have any effect. So that's column number 0. So for the data vectors, I'm going to take the columns 1, 2, 3, and 4. So I'm going to select columns between 1 and not including 5. So that's simply using this command here, and the labels are, well, they're in column 5, so in the last one. So that's what I do here. So then applying this train test split, I can split it into a training set and a test set. So I choose 25% to go in my test set, and I shuffle it so it gets mixed up here. It doesn't just take it in the order it has here. So it's randomized pretty well. Then I do a little bit of fiddling around here with getting the 0s turn into -1s, and so there are definitely more elegant ways of doing that. But I just make it -1 if y is 0, and I put it equal to 1 if it's not equal. So if it's already 1. So I just make these train and test sets now, and they are now, instead of being 1s and 0s, they are 1s and -1. So let's just look at one of them. So we can, I better do it first. Instead of just talking, I just talk about it. The computer doesn't understand that I wanted to actually run the code, but if we do it now, it should be better. So you can see now that the labels are -1s and 1s, so they're mostly -1s, and -1 means no default. 1 is a default. So then we also looked at, as we said, that if you look at the magnitude of these numbers here, they're very different. So the LTI is a number smaller than 1. The income is in the tens of thousands. The age is in the teens, between 0 and 100, and the loan are in the thousands. So they're very different magnitudes, and so we want to scale them so that they sort of have the same magnitude. And so there are different ways of doing that. So in sklearn, we have a number of different scales. I'm choosing the standard scaler here. The standard scaler here, all it does is it turns them into mean 0 and the standard deviation 1. So it subtracts the mean and it divides it by the standard deviation. And so this standard scaler here is another class. So I instantiate it here, and then I can both fit it and transform x, because it has to figure out what is the mean and what is the standard deviation. So it has to do that by looking at the training data. So it takes the training data, computes the mean and the standard deviation, and then performs the transform. So it fits and transforms in one. So fit underscore transform, that does the both the computing the norm, computing the mean and the standard deviation, and also does the scaling. And then, as we also discussed, it's very important that you use the same mean and standard deviation when you want to scale the test set, because the test set, you can't compute the mean and the standard deviation. That would be cheating if you did that, because you can't touch the test set. So you have to use the same mean and standard deviation that you found in the I lost power on the meeting. Hold on just a second. Yep. So we're gonna use the same numbers there to scale the test set, and that is a great thing about the using this standard scaler, using the fact here that it's an object of this class here, because now when we fit transform on X train, then we store the mean and the standard deviation. So we just apply that to, you see here, when we do X test, we only do the transform. We don't do the fit. So let's try to apply a couple of support vector machines and see how well they perform. So first we take a linear kernel. So linear kernel, that means that we don't do any feature transformations. The feature map is the identity. And so the kernel function is just the function that takes a dot product. It takes k of x comma y is just a dot product, x times x dot y. So that gives us the linear kernel. That means there's no feature transformation. So let's see how well that performs.
And Niels, this C is the what do you call it, regularization term?
Yeah. There was the C was that term that we multiplied these.
One by lambda.
Yeah. So again, we instantiate it with a linear kernel, and C equal to 20, and then we fit it on the train set with the training vectors, the 4-dimensional training vectors, and then the labels. And let's see how well it does on the test set. So that means we're going to use the predict function on the test set to find out what labels it predicts for the data we held out. So again, we have scaled the test set using the same parameters as we computed from the train set, and we take the predicted values, and then we can look at the see how well it did by running the accuracy score. The accuracy score takes the actual labels and it compares it to the predicted labels. So it's a simple, very simple function. And we have forgotten to import the accuracy score. So that code should be somewhere up here. It is. So I better import that too. So let's see. So we get a test score of 96%. So that's pretty good. The confusion matrix. We can also see the confusion matrix here is how many. So this is -1. So that's no default. How many of these does it predict correctly? So as we can see here, there are 434 that don't default, and of those 434, it correctly predicts the 424, and 10 it mispredicts. Here are the defaults, and of the defaults, so there are 66 defaults in the test set, and of those it correctly predicts the 56 and incorrectly predicts the 10. So that's what the confusion matrix does. So if you want to, we can see how many there are of each here by using this counter here. So you can see that there, as I said, 434 non-defaults and 66 defaults. So we can also see how well it performs on the training sets, and it does worse than that's strange. Let's try the logistic regression and see how well that does. Again, I forgot to import it. This is not so good. That's up here. So let's see what we get if we use logistic regression. So I should say that the thing we did up here, that was using a linear kernel. So we're separating by a linear subspace, and we can fit. So here I do. This is obviously also a linear subspace that separates here using logistic regression. And let's see what we get here. We get actually slightly better, 96.6%. So let's finally try it with the RBF kernel. So again, the RBF kernel is a default for SVC, so I don't have to put any kernel in here. And again, I take it now. I took C to equal to be 1,000. So I have very little constraint on my C on the slack variables. So let's see what we get here. We fit. We predict. And let's see what we get. Accuracy score. So we get a substantially better result. We get 99% correct precision on the test set. So using the the RBF kernel here gives us a better result there. We could try other things if we want. We can try other kernels. By putting the keyword kernel into polynomial, if I'm not mistaken, degree equal to 2. So we could take a quadratic kernel like we did before and see what we get here. So let's
You don't have to give C here, no?
I can if I don't put any C in, it defaults to, I can, yes, I should put a C in and put a 100 in here. If I don't put a C in, it defaults to 1.
Okay.
So let's see how well that performs. So let's look at predictions. Yeah, so writing code live is not recommended. It's very easy to make mistakes.
You have to keep up the entertaining dialogue while you type, Niels.
Yeah, right. I know. It's scary. Okay, so let's see. We got. Let's see what we get for the. So we got a pretty lousy 90%, right? So even the it might be that we can mess around with the C here, maybe. So the bigger you make C, right, the less restrictive it is, because you had this the alphas have to be between 0 and C. So the bigger C you take, the less restrictions you have on. So that improved it a little bit. So take a bigger C, so puts fewer restrictions on the alphas. I get a better score. Let me try to get all the way up to 10,000. I get, yeah, it gets a little bit better. But the best of the ones we tried here was definitely the RBF that had a test score of 99%. So that's a pretty pretty good performance, right? It will correctly predict in 99% of the cases. So that.
So, Professor, so
yeah.
If we change if we reduce the restriction for the SVC with the RBF kernel, I don't think it's going to make much more difference, right? Because it's already.
No, probably not. I mean, we can try it. We can try to go up to 10,000 and see what we got. No, it probably doesn't make a big difference. We can try. If we lower it, yeah, it probably will make some difference. No, actually, but it made it better. So I don't know. That's kind of strange. Let's try to make it much smaller. Now that may, so it's again it's a matter of if you restrict, right, then again you have you prevent overfitting a little bit. So if you make it make C very small, then you restrict your alphas, and that will tend to you restrict your or to alleviate overfitting. So if you take well, that's not good either. Yeah, so it looks like C equal to 1. Again, you should of course do a grid search here to find the best. Now, what we're doing here is absolutely, of course, is illegal because we're trying to optimize C on the test set, which is something we must not do. So it's completely illegal what we're doing here. But
you converted your test set into your training set.
Yeah, well, that's yeah, right. But I should not I should have a validation set and try to optimize on that and then look and see. But as you can see here, the support vector machine with RBF kernel performs pretty well on this data set, and it's yeah, it's a very good classifier.
So one question here. Go ahead.
Yeah.
Sorry, Niels, is that a statement about this data set, or is that a statement about the radial basis function generally doing better?
Well, I mean, it will certainly fit the training set better because I mean here in sklearn it optimizes the variance and the length scale automatically. This sigma squared and this L squared. So it also finds the best ones for those. So it is a very flexible. It's a very flexible kernel that allows you to. It basically allows you to separate any training set, but that we know does not necessarily mean that that is going to predict well. But what you get here is when you use the RBF kernels is that the separating the decision boundary is going to be a smooth curve.
Yeah.
So that is a good thing. I mean, you're not going to get some very strange curve that has kinks and what have you that just tries to fit the training set, but the RBF guarantees that the separating the decision boundary is always a smooth. In this case, it's not a curve, but a smooth manifold, as it's called. So that tends to make sure that it doesn't overfit too badly, and so that's why I think the kernel, the RBF kernel, is pretty good. There are a number of other kernels that also do a very good job, and there are some very complicated ones. But you can literally make thousands and thousands of kernels. It's very easy to make kernels. If you have kernels, if you take two kernels and add them, you get a new kernel. If you take two kernels and multiply them as functions, you get a new kernel. So you can really make lots and lots of kernels. So it's very easy to make all kinds of kernels, and there are general ways of making kernels that can, and so it's it's in some specialized data sets, you might be better served by taking some pretty exotic kernel and try to do that. But I can't give a real sort of rule of thumb for how to do it. The RBF kernel works pretty well in most cases, but there could be some exotic cases where it wouldn't work so well. But the main thing about the RBF kernel is that the decision boundary is a smooth thing. Yeah.
Yeah, I think it's a pretty cool idea of mapping from n-dimensional plane to a high-dimensional plane for separating.
Yeah, it is.
Came up was a very cool idea.
Yeah, it's a very cool. It's actually a beautiful idea. It's very ingenious. So it was yeah. It's beautiful, beautiful math.
So Niels, what does the algebraic geometer in you see that we can't see?
Well, I mean, I can't see into 4 dimensions, but I think it's I mean, I enjoy the what can I say, the cleverness in the idea here, right? The fact that you see that the problem, the optimization problem you get only depends on the dot products between the vectors and not on the vectors themselves. And that's a really interesting observation. I mean, this is done by a Russian named Vapnik. He was working at.
Is he the professor at Columbia University?
No, he was. I think he was working at IBM, if I'm not mistaken. I mean, this was done in the 70s, I think, 60s or 70s. It's not that old.
Yeah, I know. There's a guy who did who came up with SVM. He came for presentation at our firm, and
did he? Okay.
He's a Russian guy. He has a book on SVM as well, and he's a part-time professor at Columbia as well. So
okay, but yeah, I wouldn't be surprised. But he must be pretty old now.
Yeah, he was pretty old.
Yeah. Okay. Yeah. Yeah. It's a. I mean, it's a very nice idea. The only problem is that it doesn't scale so well. So if you have these enormous data sets, you're not gonna be able to use it because it's simply too slow. I mean, some of the algorithms to perform the optimization. I mean, there are quadratic optimizers, so there are software packages that does it, but they really don't work well when the data set becomes big. They can't do it, but there are other sort of approximate that constructs sequences. There's something called the SMO, sequential minimal optimization, which is a pretty clever idea in the sense that it says, well, we can't optimize one alpha at a time, because if we change one alpha, then we're going to minimize we're going to ruin the constraint. So this constraint that the sum of the yi's times the alpha i's are equal to 0. So if we just change one of the alpha i's, then we're gonna violate that constraint. So we can't do that. But the idea is that we're gonna change 2 of them at a time. So if we take 2 of them and we keep their sort of the relation. So they take y1 and y2, or alpha 1 and alpha 2, and we keep the condition that y1 alpha 1 plus y2 alpha 2 is equal to some fixed thing. We don't change that particular number. We can change them amongst each other so that their relation is still satisfied. And you can use that to optimize solve this optimization problem. And there are a number of what can I say, some more, some less clever ideas of how to select the pairs of alphas that you're going you're going to optimize, and that you if you just try to do the randomly, you can do that. You can randomly select pairs, but that is not the best way of doing it. There are other ways that are much better, and makes it converge much faster. So,
But Niels, there's also, I guess, intuitively, I feel that it's unclear that having large amount, if you're really trying to isolate a hyperplane,
yeah.
it's not like you're better characterizing the hyperplane by adding a lot of extra points.
No, but you don't want to. I mean, it's not necessarily adding them. I mean, it's. I mean, if you,
No, I'm just making a silly example where, let's say, the dividing boundary is the y-axis,
yeah.
and if I add a billion
No.
points into this
Yeah.
problem, it makes the optimization slower.
Yeah, but I mean,
the same.
again, yeah, but if you start out with a data set, you really, and if it's a high dimensional data set, you really have very little idea of what it looks like. You can certainly try to do things like projecting it down to lower the dimension. So I mean, there are ways to
I'm talking about
project.
not the number of features, but the number of points, number of sample data points.
Yeah, but again, you need to sort of, if you want to do that, then you need to have some idea of where your separator is, to know which ones you can throw out. If you don't,
But I was saying, suppose let's say you have 10,000 points and you randomly picked 5,000. I'm just making a scenario.
uh-huh.
And you resample the 5,000 again, and you find that your hypersurface is fairly stable. Or you did 5,000.
Yeah, sure, you could do it like subsampling. Yeah, you could try to do that. That's yeah.
So then you could argue for certain data sets that just because I have 10 billion points, I'm not really making the hypersurface any better by throwing a lot of points and slowing
No,
down.
but I mean that's I mean that'll depend on the data set, right?
Yeah.
So in some data sets that could possibly be true.
Yeah.
By subsampling, you could get pretty good results.
Yes.
That's possible.
There's one technical question. Is there an easy way to see which kind of kernels will produce smooth hyperplanes in the projection? Is there a criteria on the kernel?
Is there what?
Is there a criteria on the kernel that will say that this type of kernels are likely to produce smooth?
Right, there is. I mean, if you take a polynomial kernel of degree n, then it'll be smooth up to degree n. I think, if I'm not mistaken. So they will give you decision boundaries that are smooth up to degree n. So it has continuous partial derivatives up to degree n. And the RBF, you can sort of view that as a infinite polynomial infinite degree. So that'll be called C infinity. They'll have derivatives.
Any C infinity function could work, but does it? So what? I'm trying to understand what are the criteria. Like that also looks like a function with compact support of some kind, right? Because it's exponentially damped.
It does not have. I mean, it's non-zero everywhere, but of course it's depending on the length scale there. It drops off very quickly.
Yeah.
So it will tend to so if you start with one point and look at what it looks as a function of another point, it will drop off pretty quickly as you take points further away from the fixed points. So depending on the length scale. But yeah, I mean it's
that is a beautiful function. The radio.
Yeah, it is. RBF. Yeah, it is. I mean it's like a Gaussian, right?
Yeah.
But you can try other. I mean you can certainly try many other things. So.
And Niels, one unrelated questions.
Yeah.
He talked about least angle regression, LARS, right? Do we have that as a standard method in scikit-learn or no? Where
What was it called?
it's called LARS, least angle regression, where you regress against the first variable which has a maximum correlation with the y, and take some multiple times that first variable, so that now the correlation between the first variable and the residual of the first variable and second variable.
I don't know. I haven't seen it. There's probably some package that can do, but I haven't seen it.
Okay.
I'm not a big fan of such methods, to be honest. So it's for economists to use that kind of method. So,
yeah, Professor, in the example with that 4 data points that you used to explain,
right.
when we flip the labels for the top 2 points, right?
Yeah.
Still, we were not able to converge to a solution, right? Why would that be? I thought.
No, if you flip, then it should be.
No, then it became singular. Last time when we were doing
it became singular. Yeah.
When the data points were flipped, it was coming after a few iterations. It was not converging. We did that using the logistic regression.
Yeah.
Yeah, I mean, they would become singular because there would be if you don't regularize it, right?
Correct.
So if I flip the 2 points here, right, the labels here, right, then it obviously becomes separable.
Yeah.
Right, but then if it's completely separable, then logistic regression will not converge. So there you need to regularize. But if you regularize, you'll get a solution, right?
Yeah, I thought, Manish, we were running the regularized Hessian.
Yeah, I think we have to look at it. We were running regularized one because it was the Hessian was regularized Hessian, right? And the gradient was also regularized. So it was still getting into singular case.
Right. I mean, when you
I'll send you that note. It's the one. It's your notebook from previous one.
Yeah. So you did that not work? Did you not get a solution? And,
you used the Newton descent method where it was like the gradient times like Hessian inverse.
Right.
And then that part, I think the code for Hessian was getting singular, right? Tejas? I think so.
Yeah.
Yeah.
Oh yeah. Well, that's very possible. Yeah, I mean the thing is that the loss function you get there is, I mean, I think I showed a picture of the loss function, right? It becomes very close to being linear as you go further away from the minimum. And so if you're far away from the minimum, the loss function is, if you get further away from the minimum, the loss function is almost linear, and that means that the Hessian is going to be 0. Right, the double derivative of a linear function is 0. So that's something you definitely have to watch out for. If you're very far away from the minimum of the loss function, then Newton's method will probably fail because of the. You can try to use which is the BFGS. Minimizer. That should work in the sense that it's similar to the Newton's method. It converges very fast, but it does not try to compute the Hessian. It approximates the Hessian, and as you go further along in your sequence, it gets closer and closer to the Hessian. But it's also a very clever observation, and the observation is you don't really need to compute the Hessian, because all you need to know is the value of the Hessian, of the inverse Hessian, on one vector, namely the gradient. Right? You don't need to know the whole hashing. You just need to compute it on one vector, and that's that can be used to construct an algorithm that is almost as fast as Newton's, but doesn't fall into those problems. So this is the BS, I think it's called, Broyden Goldfarb, whatever. So that's basically the standard algorithm that everybody uses. So that's also an SK-learn.
Thanks a lot, Niels.
All right. Okay.
I think
so much, Niels.
try these methods.
What's that?
I'll try to find some data sets where I'll see.
Yeah. Oh, for sure. Yeah.
I'll
Yeah.
let you know next week how it does.
It sounds great.
Yeah.
I look forward to it. Okay.
Okay.
Thank you so much.
Thank you so much.
Okay. Sure. Take care. Bye-bye.
Bye.